Thank you very much, and thank you for the kind invitation. So, welcome to the second part on the synchronization dynamics of cilia and flagella. And before we start, so I will dive into theory, but then dive out again. To then dive into a second topic and dive out again. So if you get lost, don't be afraid. There will be a point to re-enter later. And also I try to be a bit more slowly on those parts that I hope are of general interest, and maybe a bit faster on more specialized topics. So we've already seen in the talk of Prerna Sharma, the beating of cilia or eukaryotic flagella. So these terms are essentially synonymous, that propel micro swimmers in a liquid. And this cilium or eukaryotic flagellum is actually a bestseller of nature. So very many eukaryotic cells possess cilia. We have seen examples of sperm cells. Prerna showed examples of the green algae Chlamydomonas that swims with two flagella. She showed example of cilia carpets that line the epithelia, for example, of our airways, where they clear debris and pathogens from our airways by their collective beating. But they are also eukaryotic pathogens, like those responsible for malaria or sleeping sickness, that propel in the bloodstream of the host with a eukaryotic flagellum. So what makes the eukaryotic flagellum beat in the first place? I'll be short on this. We have been seeing a beautiful exposure on this topic by Prerna. So if you cut through a cross-section of cilium, there's a highly regular symmetric cytoskeletal scaffold, the axoneme. So you see here cross-sections through microtubule doublets that run all along the length of the flagellar axoneme, and has a characteristic ninefold symmetry. And in between these microtubules here highlighted in green, there are these red electron-dense structures. These are molecular motors, dynein motors, here also shown in red in the schematic. And these molecular motors make the cilium beat. They cause a sliding displacement, as explained by Prerna. And this is, of course, an energy-dependent process. So whenever each of these almost 100,000 molecular motors makes a single step, it hydrolyzes a single energy-rich ADP molecule, freeing 25 kBT, and part of this chemical energy is then transferred to mechanical work that deforms the flagellum. And so motor activity, the collective activity of many of these molecular motors, gives rise to a deformation of the axoneme. And it is then more or less a consensus that this geometric deformation of the axoneme in turn controls the local activity of the molecular motors, giving rise to a closed feedback loop. And different specific theories of how cilia beat can be distinguished by different mechanisms which specific geometric deformation controls motor activity. But we will not go into this today. Today, I rather want to focus on the beautiful phenomenon that together these motors drive regular periodic bending waves. So the cilium or eukaryotic flagellum runs through a periodic sequence of shapes And we can parameterize this periodic sequence of shapes by a single periodic variable. So like in this movie, we can match each shape of the flagellum at one time point to a position of the red dot on this abstract circle. And while the flagellum is beating, this red circle then moves, this red point moves around the black circle. And whenever one full beat cycle is completed, this red point will have also completed one full turn. And if we thereby parameterize the periodic sequence of flagellar shapes during the beat cycle by just an oscillator phase variable, then this variable, of course, increases in time, and increases exactly at a rate equal to the angular frequency of cilia beating. And this is a very simplistic but powerful model in nonlinear dynamics called phase-oscillator description. And we can look at the flagellum as an example of a biological clock, as an example of an oscillator. In my talk, I will address 3 aspects. First, I want to show that this biological oscillator, the beating flagellum, is not perfect. There's active biological noise, which actually has biological consequences. Then in the second part, I want to show that cilia can respond to external forces from the fluid. And I think that's a very interesting aspect. So Priyanka's talk already showed that the hydrodynamic friction, it's maybe not the dominant contribution in the overall force balance of the cilia beat, but still we cannot fully neglect this. Still, it plays, even if just a minor, it plays a role and is actually responsible for cilia, for several cilia to synchronize their periodic motion. And synchronization of cilia will be the third topic. And actually, I will be hopping between the third topic and the second topic as appropriate. So let's start with motor oscillations and noise. So I introduced the concept of viewing the beating flagellum as an oscillator, but actually it is not a perfect clock. It is a noisy clock, and in a more accurate description, we have to augment this phase oscillator formula, where the time derivative of the phase equals to the beat frequency. We have to augment this by a noise term. And how we can measure this noise term and rationalize about its existence, that we will address in the next 15 minutes. So what we started when we did this project 7 years back, we're starting with really high precision tracking data of a bull sperm cell. And here you can view a subsequent flagellar shapes viewed in the coordinate system of the swimming sperm cell. So we watch the flagellar banding waves in a coordinate system that moves such that the sperm head appears at rest. And you've already seen before that we can then measure at each arc length position of the flagellum a tangent angle, so we can characterize each flagellar shape as a tangent angle profile psi that depends on arc length and of course also on time. We can subtract the time average, which characterizes the mean shape of the flagellum. We are not interested in this now. We are only interested in the dynamic part, and then we can ask, can we represent this dynamic part of the flagellar bending waves by just a minimal set of numbers? And some of you may know the dimensionality reduction technique of principal component analysis. So essentially we ask, can we find two static profiles, which are called psi1 of S in blue and psi2 of S, and they are depicted here. So these are profiles of the tangent angle, tangent angle as a function of arc length S. And can we find such profiles that for each time point with a suitable linear combination of these principal profiles, psi1, psi2, that we can most accurately reconstruct the original experimental data. And that's essentially what principal component analysis PCA does. It tells you what are these profiles as plotted down here, but it also gives you for each time point these coefficients, beta 1 and beta 2, these shape coefficients. And now you see in the movie to the left, that's the time-dependent shape of the flagellum, and to the right, we are plotting the correspondent value of these coefficients beta 1 and beta 2. Gives us a red point in the beta 1, beta 2 plane. And now these, you see these points, they run in a circle. And if you ponder about this for a second, you must acknowledge they have to be, because at the end we are looking at periodic motion. So actually our red shape point in this abstract beta 1, beta 2 shape space should run along a closed orbit. Fair enough. And we can fit a limit, so-called limit cycle to this closed orbit. So this is if we average out noise, this is the averaged shape cycle of the beating flagellum, here in red. And now you see that the shape points that we actually measured, these black points, they deviate a little bit from this perfect limit cycle shown in red. And we could confirm that these deviations, they are not due to measurement errors. The tracking errors are much, much smaller. And instead, what we could confirm is that these deviations from the perfect limit cycle in red, these are genuine biological fluctuations that characterize the beating flagellum as a noisy oscillator. And there are two types of fluctuations that we can distinguish. There are amplitude fluctuations. So sometimes the black shape points, they are a bit more outward and sometimes more inward compared to the red limit cycle. And this corresponds to the amplitude of the flagellar bending wave sometimes being a bit higher than on the time average and sometimes a bit lower. So these are the amplitude fluctuations. But there are also phase fluctuations, meaning that if we track how fast these shape points run around the limit cycle, we find that on average, they move along this closed orbit with a speed given by the frequency of flagellar beating, of course. But if we look closely, we find that the speed fluctuates a bit, and these represents phase fluctuations that will later be important when we talk about synchronization of cilia. So how can we characterize these fluctuations? So one way, if you have a clock and you want to know how good this clock is that you compute its quality factor. And the quality factor essentially means if you would start at time equals 0 with a set of identical clocks, in this case of identical flagellar, and you let them run, each with its own noise, and you ask after how many cycles will the phase have decorrelated. And for an atomic clock, you find Q factors on the order of 10 to the power of 8. But for a bull sperm flagellum, we measured a value of around 40. And this characterizes the phase speed fluctuations of flagellar beating. And now you may ask, where do these fluctuations that we observe in the experimental data come from? Could it be that we are just looking at some thermally excited fluctuations? Could this be just thermal noise? The answer is no. We can use the fluctuation dissipation theorem to have an order of magnitude estimate of what fluctuations we expect for a passive flagellum. And if we compare this to the noise strength D, which is closely related to the quality factor, so if we compare this estimate for a passive flagellum to the fluctuations D that we actually measure for bull sperm flagella, we find that the measured fluctuations are 1,000 times larger than what we would expect for a passive flagellum. And this shouldn't be any surprise, because at the end we are looking at an active system. There are almost 100,000 molecular motors that each have their own stochastic dynamics, which then on a mesoscopic level give rise to this noisy flagellar beating. And we previously asked ourselves, can we theoretically understand the origin of these non-equilibrium fluctuations of the flagellar beat? And for that, we turned to a minimal model of collective motor oscillations that has been put forward by colleagues before. And it's not detailed enough to really describe flagellar beating, but it's sufficient to describe how a collection of N motors can give rise to periodic motion. And what has been previously done is that this model has been studied when N is infinity, when you have an infinite number of motors and everything is perfectly periodic. But if we run this model with a finite number of motors, we find that oscillations are noisy. And if you have a small number of motors, like here, 100 motors in this minimal model, fluctuations are really very irregular. And if we increase the number of motors to the right, we have 10,000 motors, then oscillations become more regular, and we can work out this minimal model because it's so simple analytically and find indeed that the noise strength D that characterizes these noisy oscillations scales inversely with the number N of molecular motors assumed in this model. So the more motors N you have, the smaller is the noise strength. And now for the theory aficionados among you, I will quickly go through the model. So we assume there are molecular motors, N of them attached to a filament. That could be one of these microtubule doublets in the flagellum axoneme, and they can bind to a neighboring filament, and they can also unbind with respective rates omega on and omega off. And whenever a motor is bound, it feels a periodic interaction potential, and this potential reflects the periodic nature of these cytoskeletal filaments, which are composed from monomer units. That gives a natural periodicity. So the bound motors, they feel this interaction potential, which exerts a force on this green filament. And then the blue filament and the green filament, they're coupled by a visco-elastic element here. And if you then let this model run with these ingredients, you get spontaneous oscillations. And this is like a minimal model of how a large collection of molecular motors can drive spontaneous oscillations, similar to what happens in the flagellum axoneme. And with this model, we can then analytically find that the quality factor, which is the inverse of the noise strength D that we had before, that the quality factor scales with the noise strength, with the number N of molecular motors. And we think that this minimal model can at least give qualitative insight to this, to the noisy flagellar beat of sperm cells. That would be our model system 1 here. And we can make a corresponding plot in a diagram where we have the number of motors on the x-axis and the quality factor of noisy oscillations on the y-axis. But this generic minimal model also applies to other motor systems. For example, in our ears, they are hair bundles that we use to detect sound waves, and this is actually an active sensing unit that can oscillate itself. And also there we can look how many motors are there and what is the quality factor. And the third system has been realized 10 years ago at the Institut Curie, where an in vitro system of molecular motors coupled to a bead trapped in an optical trap was used to generate an in vitro oscillating system, and that would be our model system 3, which we again can assign a point in this plot, motor number versus quality factor. And we know the model is simple, but at least this qualitative trend is captured by the different colored curves, which are predictions from this minimal model, where we vary one essential parameter. So that was the first part, introducing the flagellar bead as a noisy oscillator. And of course, you can ask, is this flagellar noise something that only theoretical physicists find interesting, or is it actually relevant for biology? Well, the first example is shown here, that of course, if the flagellar bending waves are noisy, then swimming will attain a stochastic component. And what we show here is a simulated swimming path of a bull sperm cell, where we put in exactly the same noise, flagellar noise, in the simulation that we have previously measured in the experiments. And from that, we can estimate an effective diffusion coefficient from these swimming circles of these sperm cells. And the predicted value of 3.3 microns per second is at least on the same order of magnitude as a previous experimental measurement by Ingmar Riegel-Kruse, which observed 9 micrometers squared per second.
Benjamin,
Okay. And with
Benjamin,
there are a number of questions.
Can we take few questions now?
Sure.
Okay. So there's a first question by Amit. Can you unmute yourself and ask the question?
Yeah, yes. Actually, in the first movie you showed, like maybe I have missed. So, like, are you taking into account the translational motion of the flagella also? Like in movie, I could see only the oscillatory motion of the tail. So, what did you?
So maybe I was too quick on this. Of course, in the experiments, we see these are free swimming cells. We see how the flagellated sperm cells move through the field of view. But then for the analysis, we switch to a co-moving coordinate frame. So consider coordinate axis that you glue to the sperm head. And then we first plot the flagellar bending waves in this co-moving frame, where the sperm head is always at the origin of the coordinate system and always has the same orientation.
Okay.
So Vijay, you can ask the question. Your question.
Yeah. So Benjamin, in the model, you showed the noise strength. I presume this is some second moment that you're showing. Can you also calculate the full distribution of the noise? Is it Poissonian?
No. What is Poissonian is indeed the stepping of an individual motor. The binding and unbinding dynamics of an individual motor is indeed Poissonian. But if you look at a large collection of many motors, it is like applying the central limit theorem. And in that case, the distributions are approximately Gaussian. And in the analytical calculation we actually make this assumption. Everything is Gaussian noise. And with that assumption, we can then do the calculation.
But even for small n that you showed, the Gaussian is good enough, is it? The n like 100 and all?
Yeah. For that, really, assuming that it's Gaussian is good enough.
Okay, thanks.
So Prerna, you can ask your question.
Yeah. This limit cycle shape that you have got in the beta 1, beta 2 space, it's elliptical. It appears to be elliptical and lopsided. So is there any physical significance? Like, is it related to the fact that the shape is not average shape is not symmetric, or something like that?
No, because we subtract the time averaged shape of the flagellum at the beginning. So the asymmetry of the flagellar bead should not play a role.
Yes.
You do have effects like the amplitude of the flagellar bead is not constant along the arc length of the flagellum. It increases from the proximal to the distal end.
Right.
Still, I wouldn't over-interpret this, because you can, I said we use a co-moving coordinate system, and there are different ways to do this, and then these limit cycles always look a bit different. None of the conclusions would change.
Right.
But this particular shape of the limit cycle may change.
Okay. Thanks, Benjamin.
So Benjamin, I have a quick question. My question is, in the theoretical analysis, you showed the dynamics of this relative dynamics between two filaments due to the molecular motor motions, right?
Yes.
But that in the flagellar motion, when you are actually looking at the rotational motion of the flagella, so there is so this one-dimensional dynamics between the relative motion that gets translated into rotational dynamics, so via some bending modulus of the flagella. So those should give rise to new time scales in the rotation or not.
I'm not sure. So first of all, the biological example I showed here of the eukaryotic flagellum of sperm cells, that is an almost planar bending wave. So we look at just a local curvature of the flagellum that gives rise to these planar bend shapes. And Brenner explained in her talk how a sliding displacement of filaments can give rise to, because they are attached at the base, actually gives rise to bending of the cilium. Maybe I can quickly go back to that.
I was wondering the bending.
Yeah, so the motor activity gives rise to a shear displacement, and because the filaments are attached at the proximal base, this shear displacement at this position can only be accommodated if the whole structure gets bent. And of course, in a full exoneme, you have 9 microtubule doublets, so you need more complicated models, but still the bending stiffness is highly anisotropic, so it's much easier that the whole structure bends in one direction than in the transversal direction. And this actually selects then the beating plane of the flagellum. And there's a rich and as a bottom line, these models with just 2 filaments instead of 9 filaments that do not have this full 3D geometry, they can already semi-quantitatively capture a lot of the physical phenomena.
Thank you. So I don't see any further questions, so you can go ahead with the rest of the talk.
Okay, so before I want to come to the second topic of Cilia load response, I actually want to give you a sneak preview on the third topic, giving previous work on synchronization, because that is actually the motivation why we looked at the Cilia load response, the second topic, in the first place. So we'll now review some classical experiments and basic theory. So we've seen swimming sperm cells. Woolley reported if 2 sperm cells actually accidentally collide with each other, they may synchronize their bending waves. In a second example, Ingmar Riedel-Kruse observed that at very high density of sperm cells, suddenly the sperm cells organized into a hexagonal array of sperm vortices. And in each vortices here, shown as a schematic, the different sperm cells synchronize their flagellar bending waves. So they go with a common rhythm. Here we see a multiciliated organism, a multiciliated green algae, that consists of many chlamydomonas-like cells, and each light green dot here, that's one cell with 2 cilia, and these cilia all beat with a common frequency in a coordinated fashion, and really looks like a Mexican wave in a soccer stadium. And here below we see a quantification of this metachronal wave. So as a function of the polar angle that runs around this spherical cell colony, flow was measured as a function of time. So the horizontal axis is time, and the vertical axis, that's this polar angle. And you see not only there's nice periodic motion, but the motion at different polar angle positions is coordinated, giving rise to traveling waves of cilia activity that run on the surface of this green algae. And you do not only have this in green algae, but actually we have it in our airways, where airway epithelium is densely packed with thousands of cilia that also beat in a coordinated fashion, for example, to clear pathogens from our airways. And they are not only found in airways, also in the brain ventricles. There are cilia carpets. In the oviduct, the fallopian tubes are lined with cilia carpets. And then there are more microspheres like the paramecium that has cilia carpets on its surface. And also for paramecium, metachronal coordination is observed, synchronization is observed, allowing these unicellular paramecium to swim fast. So how can these cilia synchronize? There is no master clock, there is no global pacemaker. And already almost 70 years ago, Sir Taylor put forward the hypothesis that one cilium may actually feel the flow field generated by its nearby cilia. So one cilium bead sets the surrounding fluid in motion, generates a long-range flow field that propagates, that's felt at a second cilium. And Sir Taylor hypothesized that these direct hydrodynamic interactions may synchronize cilia. And then it took until 2014, when in a landmark experiment, Brumley could show that indeed direct hydrodynamic interactions can synchronize cilia. And in these beautiful experiments, 2 ciliated cells were held in separate micropipettes at a distance, and then they're synchronized, ruling out any direct mechanical coupling through distal fibers or alike that may exist if you would just look at a single cell. So what are these hydrodynamic interactions? A short physics primer. So you might know at low Reynolds hydrodynamics, which is relevant at the scale of these cells. If you would move a small sphere in a fluid by a force F, you have a linear relation between the force and the velocity at which you move the sphere. And if we would now have a second sphere, then we find that the velocity of the second sphere here depends not only on the force F2 that you apply directly to the second sphere, but it also depends on the force F1 applied on the first sphere, although much weaker, because the force applied to the first sphere generates a long-ranged flow field that propagates to sphere number 2, and this propagation is described by this blue function G, so-called Oseen tensor here depicted in gray, and that is how motion of sphere 1 affects the motion of sphere 2 by direct hydrodynamic interactions. And this is again data from the Brumley experiment with the 2 monociliated cells held in micropipettes at a distance. And there they could also record how the synchronization between the 2 cilia, how the synchronization strength depends on the distance d between the cilia, and they observed an inverse dependence, a reciprocal dependence as 1/d, as predicted by theory. And it has been discussed a lot in the community to which extent these direct hydrodynamic interactions are also important for the synchronization as observed in cilia carpets that form these metachromal waves, as well as in these little green algae, chlamydomonas. And in fact, before I come to this more complicated system of cilia carpets, let's start with something simple. Let's do our homework first. Let's first do the hydrogen atom of synchronization research. Let's look at chlamydomonas before we look at the more complicated cases of cilia carpets. So this is a movie of a swimming chlamydomonas cell. We've overlaid already our cilia tracking in red. So you see it really swims like a breaststroke swimmer, and the left and the right flagellum is in synchrony, which should surprise you because there's no global pacemaker coordinating the left and the right flagellum. And you've seen each flagellum is a noisy oscillator. So if there would be no coupling, they would lose any initial synchrony. And Rimmet Goldstein in Cambridge did beautiful experiments, really quantitatively characterizing synchronization in chlamydomonas. And here's one of his plots where you see as a function of time the phase difference between the left and the right flagella. And you see initially it's 2 pi, so the 2 flagella are in synchrony. And then at some point, one flagellum takes an extra beat. So-called phase slip occurs, but after then the 2 cilia are in synchrony again, and the phase difference is 0 after this phase slip. And this phase slip is actually very likely a cause of the active fluctuations of cilia beating that we've encountered before. Now, how can we understand synchronization in a pair of oscillators in the first place? So now comes a thought theory primer. The term synchronization was first coined by Higgins when he observed 2 pendulum clocks. And at that time, 17th century, pendulum clocks were notorious inaccurate, and that for hours and hours, 2 clocks were swinging in perfect synchrony was absolutely unexpected. Actually, Higgins was laying sick in bed at the time, and he had really time to observe the pendulum clocks for hours and hours, and they always were synchronized. And Higgins got curious and finally realized, okay, they are both supported by the same wooden beam. So there's a mechanical coupling between the clocks. And you can actually redo these experiments at your home. Instead of pendulum clocks, you can use standard metronomes like musicians do. Put them on a table, put 2 soda cans below. And here, that's a small student project where they did this. So they put paper in front of the metronomes to make the image analysis easier. And you see, indeed, the 2 metronomes synchronize, their phase difference go to 0. And if you look very, very closely, you find that this tray actually moves while the cilia are getting into synchrony. So it is important that they are on the same tray that can move to the left and right, and which thereby transfers momentum from one to the second metronome. So that's a beautiful experiment you can do yourself, and there are also nice YouTube videos on that. And how can we describe that theoretically? So again, we have the left metronome, the right metronome, we describe each as a phase oscillator. So we have a phase phi L for the left metronome, and its time derivative is given by the intrinsic frequency omega L of the left metronome. And then there could be some general coupling function that depends on the phase difference between the left and the right metronome. And we have an analogous equation for the right metronome. And this equation actually was invented by Adler. And you may not know Adler, but you know his inventions. He was studying synchronization of electronic oscillators, and he was the inventor of the remote control shortly after World War II. The coupling function could be very general, but we stick to the simple case where it's just where we just look at the first harmonic and we assume that's just the sign of the phase difference, because obviously, being a physical function, must be a 2 pi periodic function in the phase difference between the left and the right flagellum. So let's just take the sign. And now if we have these 2 equations, we can actually subtract them, and then we get an equation for the phase difference delta of the 2 oscillators. And this equation depends, for the phase difference delta, depends on the frequency mismatch between the 2 oscillators, and there's an oscillator coupling, and you can see the 2 as 2 competitors. So the frequency mismatch wants to get the 2 oscillators out of synchrony, and the oscillator coupling tends to bring them back to synchrony. And of course, in the general case, there will also be noise. And you can, the dynamics of this Adler equation, you can nicely visualize in terms of motion in a potential landscape. So instead of looking at these equation down here in the blue box, we can say analogously, let's look at a small particle, and it moves in an overdamped fashion in a periodic potential. And then you see if this coefficient lambda is positive, the synchronization strength is positive, then our potential would look like this. And then you see here the synchronized state with a phase difference 0 is a stable state. And in contrast, if the synchronization strength would be negative, your potential is flipped. And then the perfect in-phase synchronized state would actually be metastable. The smallest perturbation will kick you out of the state, and instead you will reach an anti-phase synchronized state where the 2 oscillators still have phase-locked oscillation, but now they will have a phase difference of pi. If you add noise, then your little ball will not just go to the bottom of the valley, but will actually fluctuate there. And once in a while, there will be such a strong stochastic kick that you will be kicked over this potential barrier. And you can actually nicely compute how the frequency of these so-called phase slips, of these being kicked over potential barrier, how this goes up as a function of the noise strength on the horizontal axis. And if there's a frequency mismatch, well, you can still stay in this picture. Now you have to tilt your periodic landscape, and it gives you a small phase shift, but you would still synchronize. But of course, now it is much easier if there's noise to be kicked over the barrier to the right. If your frequency, finally, if your frequency mismatch becomes too large, if it becomes larger than the synchronization strength, then there's no synchronization anymore. There's still some coupling, and the the slower oscillator still tries to catch up with the faster oscillator, but it doesn't manage. And then the phase difference between the oscillators will actually increase forever. And so that's the basic picture. And this basic picture is actually very useful when we want to understand synchronization, for example, in cladmiomonos, because we can say the beating of a cilium, these periodic bending waves, that we can map on a phase oscillator. And previously, people have been even more extreme with the approximation and said, well, each point of the cilium moves on a closed orbit, so let's just replace the whole complex cilium by just a single sphere that moves on a circular orbit. And then you can ask, if you have two of these spheres and they move on periodic circular orbits, will they synchronize by their hydrodynamic interactions? So in this case, they are, of course, hydrodynamic interactions. And the answer is, in this minimal model, the two spheres, they feel each other, but they don't synchronize yet because the system is too symmetric. And now this was something for the theory aficionados. We have so-called PT symmetry, parity time symmetry. Essentially, it means we can make look at the spatial mirror image of the system of the two hydrodynamically coupled spheres. And of course, if we look at the spatial mirror image, nothing should change. If they synchronized before, they will still synchronize after looking at the mirror image. If they didn't synchronize before, well, after mirroring, they will synchronize neither. But at the same time, we could look at the time reversal. Now we let time run backwards. And now, of course, if before the two spheres synchronized, after the time reversal, they won't synchronize anymore because synchronization means you start with a perturbation and the perturbation gradually decays. But if you reverse the time error, it means that your perturbation would grow in time. And now you can show that for this minimal system, the spatial mirror image and the time reversal with time error flipped are just the same. So in one case, synchronization doesn't change. In the other case, the synchronization behavior is exactly reserved. So we conclude no synchronization in this minimal model. And I explained this because there's a rich literature on these minimal synchronization models, and all the different synchronization mechanisms that have been proposed so far can be classified as one or the other way to break this symmetry. You have to break the symmetry. So just mention the first one, wall effects. Of course, if we put a wall here, a boundary surface, then the mirror image will look different because we also have to mirror the boundary surface. And before I go back to biology, I want to ask if there are questions.
So Vijay has a question. Vijay, can you ask that?
No.
Okay, so yeah, it was.
Sorry.
Okay, then I can just continue. So the point I want to make is we can characterize a beating flagellum as a noisy oscillator. And if we ask how such noisy oscillators synchronize, we have a very generic equation for the phase difference delta between the two oscillators, the so-called Adler equation. And in that Adler equation, we just assume there is some mechanism that couples the two oscillators. We just put it in and say there's some synchronization strings lambda. And now I want to dive into what are really the physical mechanisms of this oscillator coupling, and can we actually compute the synchronization strengths lambda from first principles. And for that, we have to talk about the load response of cilia and flagella. So I put forward this hypothesis that cilia respond to external flows. that they feel the flows generated by the neighboring cilia. And we wanted to understand how cilia respond to external flows. What is the load response? So now, keeping with the simple picture of a phase oscillator, where we have on the left-hand side the phase speed, the change per unit time of the phase variable phi, this would now be equal to an intrinsic frequency omega naught, but now there would be an additional term, a load dependence, depending on the load. And you may think of this like, if I go up a steep hill with my car, I automatically go slower because there's more load on the engine, and we expect something similar for cilia. And we teamed up with some experimentalists, because I'm just a theoretician, and they put chlamydomonas in a microfluidic chamber. So here you see the microfluidic chamber. Here you see a micropipette, and this little region of interest, that's chlamydomonas cell showed enlarged here. And what you see now rotated, without flow, this chlamydomonas is beating nicely in a synchronized fashion. And then the experimentalists can switch on a controlled microfluidic flow. And the two cilia still beat, but we can now quantify if anything has changed when we compare the left no flow and the right with flow. And for that, we again use these principal component analysis that I introduced at the very beginning of my talk for the bull sperm cells. So again, we track the cilia of chlamydomonas at each point in time. We get the arc length, tangent angle profile as a function of arc length and time. We do the principal component analysis, and at the end of the day, each movie frame and each cilia shape in a movie frame is mapped on one blue point in this abstract shape space. And as time progresses, you run around a closed orbit, just as we've seen previously for the bull sperm cells. So it's the same method. And you see, since we can here define the perfect limit cycle, we can, to each movie frame, we can assign a phase value phi and say, in that movie frame, the cilium is in that phase phi of its beat cycle. And once we have this, we can also compute what is the phase speed at a particular time point in the movie. And then we can ask, how does this phase speed depend on the load, here characterized by external flow? So we have here on the horizontal axis the flow rate U, so that's the flow that's flowing against the chlamydomonas cell. And then for two phases of the cilia beat, in blue, the effective stroke of the cilia where the cilia move down, we can ask what is the phase speed, and also in green for the recovery stroke when the cilia move up again. And if there's no flow, then the phase speed is normalized to 1 in both cases. But if we then apply this external flow U, you find that in blue for the effective stroke, the cilia beat faster. And this should make perfect sense because the cilia are moving down and they get tailwind from the external flow. So the hydrodynamic load is decreased. It's like going downhill. The cilia beat faster. In contrary, in green, during the recovery slope, the cilia move up. They are moving against the external flow, so they're experiencing headwind. It's like going uphill, and we see correspondingly that the cilia beat slower. And we can measure this the slope from these curves, the slope chi, for each phase of the flagellar beat. So on the horizontal axis, we now have the phase of the cilia beat, and then in blue we plot a fitted slope for the curves I've just shown for each phase. And you see, yeah, during the effective stroke, when the cilia move down, this slope chi is positive, and during the recovery stroke, this slope is negative, as we expect. And we also have a very, very simple theory to rationalize this observation. And this theory looks as follows. We say, well, we are already visualizing this periodic cilia bead as a point moving on a circle. So we can just say the motion of this point on the of this black point on this gray circle should be determined by a force balance, a balance between an active driving force Q in blue that pushes the black point around the circle. So this force is always tangential. And then there's a friction force, a dissipative force in red. And the force balance between the two, that determines how fast the black point moves. And you can imagine if for some reason these friction forces, they're equal to a friction coefficient gamma, actually it's a matrix, times the speed q dot of the phase, but also other degrees of freedom. And you can imagine if the q stays the same, if the driving force stays the same, because that's an intrinsic property of cilia beating, and because we increase the hydrodynamic load, this gamma increases, then the q dot, the phase speed, has to go down. And there's one interesting feature of this minimal model that provides a bridge to Prerna's talk. Namely, we are talking about dissipative forces, and that's closely related to hydrodynamic dissipation. So if you just multiply these forces by the rate of change of the degrees of freedom, this has units of watts. This has units of energy dissipated per unit time. And now we can ask, what are sources of dissipation inside the beating cilium? Well, first of all, there's an internal energy reservoir. That's the ATP, the chemical fuels the molecular motors run on. And we can give numbers. So that's approximately 10,000 ATP molecules used per cycle, corresponding to chemical energy that's set free of 50 femtowatts. So that's the energy input. And now this energy ends up at two places. So of course, there's work performed on the surrounding fluid. When the cilium changes its shape, it sets the surrounding fluid into motion, and it performs work on the surrounding fluid. So that's the hydrodynamic part of the dissipation. But on top of that, there's the internal dissipation, where Brenner showed that this is actually the dominating contribution. And this is just heat generated inside the flagellum. It's like you drive with your car and the motor heats up. That is inevitable if you have an engine. And of course, it doesn't get you nowhere if your motor heats up. This is just lost, but it's inevitable. And in our minimal model, we have a single parameter. We have an efficiency iter that characterizes the splitting of energy flow, how much energy that is drawn from the internal energy reservoir is actually converted into work performed on the surrounding fluid. That is a fraction iter, and the rest is dissipated inside the flagellum, amounts to internal dissipation and heat generation. And this mechanical energy efficiency iter, that's the single fit parameter of our minimal model. This iter, and we find if we fit our theory to the experiments, a value of about 20% of 0.2, and at least that is consistent with previous measurements of ATP consumption. So how much energy is drawn from the internal reservoir, where previous researchers reported values between 10% and 34%. Why is this energy efficiency so important? Well, this energy efficiency tells you what role do hydrodynamic forces play in the force balance of flagellar beating, and it directly tells you how strongly will your beating flagellum respond to a change in hydrodynamic load like an external flow. So if you would have a hypothetical energy efficiency of 100%, then your cilium would respond very, very sensitively to external flow. If instead you would have an energy efficiency of close to 0, your cilium would hardly be bothered if you change the hydrodynamic load, if you apply external flows. And the biological system seems to be in the middle between these two extremes. And as a test of our theory, we used our minimal model to predict synchronization to external oscillatory flows. So in this paper published in PRL by Coarenta and Tam, they observed synchronization of Climbenimolus beating to an external oscillatory flow. And at that time, they were arguing, maybe hydrodynamics is not sufficient and we need basal coupling, we need distal fibers. But actually, already with our minimal model, we can reproduce the synchronization behavior observed in their experiments, and in particular, reproduce a so-called Arnold tongue, which they measured. So what is an Arnold tongue? Let me walk you through this. On the horizontal axis, we have the frequency mismatch. The frequency mismatch between the intrinsic beat frequency F0, at which the cilia would normally beat, and then F is the frequency of the external oscillatory flow. And of course, if the two are equal, if you have a frequency mismatch of 0, you expect the best phase locking. And on the vertical axis, we have the amplitude, the strength of the external driving. And of course, the stronger this amplitude, the better you would expect phase locking. And indeed, for such oscillators coupled to an external periodic driving, one expects there's such wedge-shaped, such tongue-shaped phase locking regions, meaning so only inside this region there would be phase locking, meaning the larger the frequency mismatch, the higher the amplitude of the driving has to be. And in these experiments, they observed phase locking in this region delineated by these white dashed lines. And with our minimal model, we actually predict phase locking in this green region. So we get a reasonably fit for the predicted and the measured synchronization regions. And to show you why this chemical energy efficiency is important, let me show you two more hypothetical cases. So if the energy efficiency would simply be 0, meaning that internal dissipation would completely dominate the energy balance, and we could completely forget about hydrodynamic friction forces in the force balance, then we would expect a 0 load response of the cilia, and we would expect 0 synchronization. So in that case, you would only observe phase locking if you exactly hit the intrinsic beat frequency. On the contrary, if you would have a chemomechanical energy efficiency of 1, if you would have an energy efficiency of 100%, so the chemical energy stored in ATP is completely converted into work performed on the fluid. In that case, the cilia would respond much, much stronger. They would be much more sensitive to external flow. And in this case, the predicted synchronization region in green would be much wider than as measured in the experiments here delineated by the white dashed lines. And if instead we use this value of 0.2 of this 20% that we previously obtained as a fit parameter from this independent experiments in the flow chamber, then we get a reasonable agreement of the predicted synchronization region, the predicted phase locking region in green, and the experimental observation delineated by the white dashed line. And this shows that this internal dissipation, which is characterized by this energy efficiency parameter, that this is really important for the load response of cilia, and thus important for the synchronization of cilia by hydrodynamic interactions. And I will be brief on this, just saying that what I showed before was for moderate flows, and then we can have this linear theory that the speed change of the cilia is linear in the applied force. But if you go to super strong flows, then there's actually a non-linear regime, and we find that sometimes cilia stall, so they don't beat anymore, or that even the beat pattern becomes non-planar and switches to a completely different mode of beating. Here we show how the beat frequency changes if we increase the flow speed, and you see first we increase the flow speed, that's the blue curve, and then some point they're stalling, but we can actually decrease then the flow speed again, and then there's first some hysteresis, but then the cilia resume beating again. And from our minimal model, we have at least a qualitative understanding of the stalling. So here the red curve, that's the theory prediction, how the frequency would change as a function of the external flow speed on the horizontal axis. And for if the external flow becomes too large, the cilia can't cope anymore with the external hydrodynamic load, and they cannot go backward, cannot go forward anymore. And but these are additional nonlinear effects which we do not understand fully yet. So before we move on, I want to ask if there are questions.
Hi, Benjamin, I had a question. In the video that you showed just a couple of slides earlier, at high flows, it looks like only one of the cilia is beating and the other one is more or less stuck. Is
Yes.
there some systematics, or is this just some initial condition that just picked out one of the cilia to beat?
There could be indeed a difference. So the two cilia of Chlamydomonas are very similar, but not identical. One is called the cis flagellum, the other the trans flagellum, and they have slightly different beat characteristics. And indeed, we observe the stalling more often for one kind of the two cilia than for the other. So we're talking here about statistics, but there seems to be a difference.
Mm-hmm. Is there some structural difference? I don't know that. I thought both the cilia are the same.
The pictures that you've seen on the introductory slides of Brenner and of my talk, on that level, they are absolutely identical.
Uh-huh.
We are really talking here about some auxiliary proteins that are slightly different. We are talking about some channels being expressed in different numbers. And so it's really a subtle difference, which, however, is important for the phototaxis of Chlamydomonas, because for that the cells have to make a directed steering response. They have to turn towards the light. And this is achieved by the cis and the trans flagellum responding differently to a calcium signal elicited by the light stimulus.
Okay, thanks.
Brenner, you have a question.
Actually, Vijay asked my question. So, Benjamin, now that you have answered that one of the cis or trans was stalling. So is the stall force of cis and trans flagella also different, or is it nearly the same?
I think they were slightly different, but we are really talking here. This is experimental data, and you see
Yes.
there's quite a spread between 5 millimeters per second and 8 millimeters per second.
Yes, yes.
And if you would make 2 bar plots for the cis and the trans flagella separately, it seems plausible that there's a difference. But this is not so clear-cut given the intrinsic variability of the data.
Okay. Okay. Yeah. Thanks.
But there are some differences.
Yeah.
Benjamin, if you don't mind, can you go back to the movie and play it again? Maybe at an intermediate speed, is it possible to pick out some differences between the 2 flagella now?
Okay, let me. This one?
Yeah, for example. Now I was wondering, at the moderate flows, can one visually pick out some difference? It's hard to say.
So again, I would say they are differences, but they are at the same order of magnitude of the normal variability of the data. So it's not that striking, but for sure, there is interesting dynamics going on here. And in particular, I would like to make the discuss the following idea. There are a number of different models how molecular motors shape the flagellar bead, and Brenner talked about this. And there's still a discussion going on details, and it's very difficult to distinguish different theories by just looking at wild-type bead pattern. And because you always have some fit parameters in every theory, and then different theories can actually equally well account for the different set of data. So I would find it very interesting if one would try to predict with such a theoretical model of cilia beading, if one would try to predict this cilia load response beyond the minimal model that we put forward. And for example, reproduce the stalling or the switching to a non-planar bead. So I could envision that in the next 10 years, this becomes a test case for theories of cilia beading. Because it makes a difference whether you only compare theory and experiment for the left case, no flow, or if you have the whole spectrum of different flow conditions probed.
Sorry, just one more question if I can ask. So in the normal physiological conditions that the clammy would face, is a flow like 3.5 millimeters per second normal, or is it way beyond what it would face?
It's way beyond.
It's way beyond. Okay.
So I think the highest flow is at maybe 10 times the normal swimming speed and more. So not outrageous, but way more.
Okay, thanks.
Okay, so I would move on, and in the interest of time, so there are so many things to talk about. But I would speed up a little bit also. So I will now summarize the whole story in one slide, but we already published this in 2013, so that's hopefully admissible. So what we showed in 2013 is that if you clamp chlamydomonas in a micropipette, then direct hydrodynamic interactions and possibly coupling through the distal fiber are important for synchronization. But if these cells are freely swimming, as they normally do, then there's actually an additional synchronization mechanism, and that goes as follows. Just imagine the two cilia were not perfectly in phase. So imagine that there's some phase difference between the left and the right flagellum due to some perturbation. In that case, the torque exerted by the beat of the left flagellum and by the beat of the right flagellum would not perfectly balance anymore. And in that case, the whole cell rotates. But now what happens if the cilia are beating and at the same time the cell rotates, then the two cilia experience a different change in hydrodynamic load. So if you look at the left cilium, that tries to move down while it's beating, but at the same time as the whole cell is rotating counterclockwise, the left cilium is additionally dragged through the fluid. So the active shape change and the rigid body rotation of the whole cell, they add up. So the left flagellum would experience a higher hydrodynamic load, and for the right cilium, the effect is contrary. The active shape change of the left cilium and the rigid body motion due to the rotation of the cell, they cancel each other. So the right flagellum experiences less hydrodynamic force. And due to the cilia load response that we discussed before, now the left cilium would beat slower because it has a higher hydrodynamic load, whereas the right cilium would beat faster because it has a reduced hydrodynamic load. And we can model this theoretically, we can measure this, and it matches. And this gives a nice mechanism of mechanical self-stabilization, where an asynchrony gives rise to a rocking motion of the cell, which then feeds back on the cilia through the cilia load response. And this closed feedback loop is tuned in such a way that it stabilizes in phase synchrony. And we can ask what happens in the presence of noise. Without noise, the two cilia would then synchronize perfectly. They would have a phase difference of 0. But if we switch on noise, then we find there's still synchronization, but now the phase difference delta, if you look at the distribution, the predicted distribution, it will fluctuate around 0. It will fluctuate around the synchronized state. And for this plot, we used the synchronization strengths that was previously measured, and that also matches our theoretical predictions. And we use a noise strength that we measured for sperm cells, and we just assume it's the same for chlamydomonas. So the cilia noise that we had at the beginning of the talk is important for synchronization. It perturbs ciliar synchronization, giving rise to fluctuations around the synchronized state and occasionally phase slips that one of the two cilia takes an extra beat. And we also have refined in the sequel, we have refined models of synchronization. So now we also include that the periodic shape sequence might slightly change due to external flows. And we've also augmented our models by including an elastic basal coupling due to the distal fibers that Brenner introduced. And then we find something interesting. If we only account for this basal coupling through the distal fibers, we actually predict antiphase synchronization. So do you see my pointer? So if we only have switch on the basal coupling, we would be here in this phase diagram, and the red colors mean that the two cilia would synchronize with a phase difference of pi of half an oscillation period. If we would only have the so-called amplitude compliance, if we would only account for the fact that external flows, hydrodynamic interactions can also change the shape of the periodic cilia shape sequence, then we would also have a red point, would also have antiphase synchronization. But if we switch on these two ingredients, then together we estimate that we are here in this phase diagram, and there everything is green. We predict in-phase synchronization with a synchronization strength that matches previous experiments. So this is just to show that we can refine the minimal models, and it shows that it can be hard to predict what happens in a model. It may be that you have one mechanism, like the basal coupling, and you have a second mechanism, the amplitude compliance. And separately, each of these mechanisms predicts antiphase synchronization, depicted here, where the two cilia have a phase difference of half a period. But if you have these two mechanisms that separately give antiphase synchronization together, you are here in the phase diagram, and you get in-phase synchronization like a breaststroke swimmer, like observed in experiments. So that was a sped up outlook on previous work on synchronization in Chlamydomonas. And we've shown that for free-swimming Chlamydomonas cells, we have this additional mechanism of synchronization by mechanical self-stabilization, that any perturbation of synchronized speeding gives rise to a rotational rocking motion of the cell, and this stabilizes synchronized speeding even if we account for active cilia noise. And in the last 5 minutes, I want to highlight a very recent work, how we can use the lessons learned from the model system of Chlamydomonas, that it's two cilia, to get a better understanding of collective dynamics in cilia carpets with many cilia. In particular, what happens if there's active fluctuations. So previous models either had very minimal descriptions like spheres moving on circular orbits, or there have been very expensive simulations running on supercomputers. And we try to get the best of both worlds by working, by describing each cilium as a phase oscillator with its phase variable phi I. And the different cilia are coupled, but we get this coupling from hydrodynamic computations. So let me show how this works. So this is a 3D cilia bead pattern from this unicellular organism Paramecium. And we can plug this into hydrodynamic simulations and, for example, compute the forces exerted by the beading cilium on the surrounding fluid. And from that, we can have a coarse-grained generalized friction force. So we have a multi-scale modeling framework. Here I'm skipping the details. The important one is we can compute the hydrodynamic interactions between a pair of cilia. And we can do this for all possible configurations of two cilia. And we do this number crunching for 3 weeks, but then we have a lookup table. And it looks like that we really can write down, okay, the friction force acting on cilia number 1, it depends on what cilium number 1 does and what cilium number 2 does, and there are these coefficients and they're tabulated. But once we've tabulated them using detailed hydrodynamic interactions, we can say, and now we say there's again a force balance between an active driving force for each cilium and the friction force that the cilium feels. And from that we get like a generalization of the Adler equation. We have the time derivative of the cilium number I, it's its intrinsic frequency omega naught, and then there are coupling terms for all its neighbors. And these coupling terms we've pre-computed using hydrodynamic computations. And then we can find what are solutions for this coupled dynamics. And indeed, we find metachronal waves that pass through the ciliar carpet. And for those who had a course in crystallography, each possible traveling wave can be characterized by a point in a so-called reciprocal lattice. So for those who are not familiar with this, just be assured that each gray dot here corresponds to one possible wave mode, and this point in the middle that would correspond to an in-phase wave where each cilium does exactly the same. And this point here with where the green arrow starts would correspond to this wave where you have wave fronts, and these wave fronts move along the direction of the green arrow. And we can compute the intrinsic, the collective frequency, and in short, for each of these wave modes, and in short, if all the cilia do the same, they're helping each other and they can beat 5% faster. But if we have something like a wave where neighboring cilia beat an antiphase, then they beat a few percent slower. That's what we predict. And another thing about this approach is that we can also ask which of these many wave modes are actually stable. If you apply a tiny perturbation, will this tiny perturbation grow or decay? And the green dots, these are actually the points, the wave modes that are stable. So you see that they're actually still a number, but just a few wave modes that are stable. And it gets even more striking if we ask, where will we end up if we start with random initial conditions? And then we find that for most, in 93% of the initial conditions will end up in this particular wave mode. And this corresponds to a so-called dexioplectic metachronal wave, where the waves, the traveling waves in the cilia carpet, move in a direction almost perpendicular to the direction of the cilia beat direction. So we have an agreement here with the experiments, and I will skip this and go directly to the final slide. So what we can now do is, as before, we account for the fact that each beating cilium is a noisy biological oscillator, and we have here on the horizontal axis the noise strength of each of these cilia. And without noise, we can quantify how many initial conditions will end up in the dominant wave, that's the green bar, and some end up in a second wave next to it, that's the blue bar. And then we can, on the horizontal axis, ramp up the noise strength and ask what fraction of time will stochastic trajectories spend in the vicinity of a stable wave mode. And we find that for moderate noise strengths, actually you spend proportionate time near the stable wave modes, proportional to the corresponding size of Besnard check in the absence of noise. And then there's a critical noise strength, and there everything breaks down. We find shortly before stochastic transitions between the different synchronized states, and the waiting times are distributed to a power law. So there's a lot of going on. We find that suddenly, I mean, it's really a very range where you change the noise strength, and suddenly all the spatial and temporal correlation functions from very high levels for moderate noise go down to very low levels at high noise, and for strong noise there's no synchrony anymore. So presumably the biological system is operating below this critical noise strength, and what we found is that really there's a very sharp abrupt transition at a critical noise strength where synchronization breaks down in ciliar carpets. And we are currently collaborating with Natalie Jokoszewski of Norway to quantify all this also in a real model system in the nose of zebrafish. And with this, I want to summarize, and I'm happy to answer more questions.
Thank you, Benjamin, for this fantastic talk. So more questions. Vijay raised hand.
Yeah. Benjamin, what do you mean by Lagrangian mechanics? I sort of lost that. I mean, it's Lagrangian in the classical sense, or in the Lagrangian in the moving sense?
No, it is Lagrangian in the classical sense, like Lagrangian mechanics. And let me start with an example. In first year physics, we learn about torques. And actually a torque is an example of a generalized force. So you can say if you have a rotational degree of freedom, I hope you can see this.
Yeah,
if you have a rotational degree of freedom, you can say, okay, this is the rotation angle is my generalized coordinate. And then I can ask, what is the generalized force conjugate to this generalized degree of freedom?
Sure.
And this is just a torque.
Yeah.
So that's first year physics. Usually in such a course, one studies only conservative systems, but there's actually a generalization of this concept for dissipative systems when you have friction forces. That's the Lagrangian mechanics of dissipative systems. That's still very classical physics.
Yeah.
And what we have done in the past years is actually extending this to active systems, where we say we also include active driving forces. And to make a specific example, looking at chlamydomonas, each cilium goes through this periodic sequence of shapes and can do so a bit faster or a bit slower. And we characterize this by this phase phi. And now we say this is a generalized degree of freedom, like your translation in classical mechanics or a rotation angle. We treat this phase of a beating cilium as a generalized degree of freedom. And once you have a generalized degree of freedom, you can talk about generalized friction forces.
Sure.
Like you have torques for rotations, we have generalized friction forces for these cilia. And we've just written a short review on this. So I'm fully aware of the fact that I've glossed over the theory details. I could just give a talk on this, but hopefully I could convey the basic idea.
Sure. No, if I can just continue. So I'm just saying Lagrangian in the sense of just deriving the generalized forces, or Lagrangian also in the sense that it will generate the equations of motion.
It gives you your equation of motions, because we say from using this Lagrangian mechanics, we find the friction forces conjugate to our generalized degree of freedom. And then we just postulate a force balance between an active driving force and these computed friction forces. So where do we get the active driving forces from? Well, we say we have a reference data set. So for example, for chlamydomonas, we had an experimental data set where the cell was swimming in nice in-phase synchrony, and reproducing this experimental reference data set with our theory uniquely determines the active driving forces. And once we have this, we can actually extrapolate to other scenarios, ask, for example, what happens if there's a perturbation of in-phase synchrony.
Okay, I'll try to look at that, or I'll write to you. I don't get it.
Yeah, please write me there.
Yeah. And you have a question?
Yeah. So Benjamin, the cell body rocking mechanism that you described, how will it depend on the cell size? Like if the size was much smaller or much bigger, will it feedback more into this? Or like, I mean, could you drive it far away from synchronization if the cell size is much bigger?
Yes, so we once did a model calculation for that, and indeed the synchronization strength, the predicted synchronization strength depends on the size of the cell body. And if you go to super small cell bodies, you can also stabilize anti-phase synchronization.
Mm-hmm. I see. Okay. Thanks for the clarification. So is this somewhere documented in your papers, or this is
Yeah, so that actually should have been in the very first paper from 2012.
Okay.
So there we have one plot where we actually, as a control parameter, we vary the size of the cell body. And yes, it has an effect on the synchronization strengths. And my take-home message here is that if you have a closed feedback loop, if you have coupled dynamics, it is very likely that you get synchronization, unless you have a highly symmetric system. But the synchronization strength itself, and even if it's positive corresponding to in-phase synchronization or negative corresponding to anti-phase synchronization, that really depends on details of the system. So you can really change details of the system, and it is robust to small changes, but once you do big changes, you can suddenly have anti-phase synchronization.
Sure. And another clarification I needed was in the phase space of amplitude compliance and basal coupling. Could you please explain to me again what is amplitude compliance? How should I think about it? Or is it the same as the rocking mechanism?
No, it's something different. So I emphasize that in Zero's approximation, we can say a feeding cilium goes to a perfectly periodic sequence of shapes, which we can characterize by a limit cycle, and we only ask, do we go slower or faster through this limit cycle?
Right.
And we also have a refined model where we look at small deviations from the limit cycle. And because there was previous theoretical work by Niedermeyer that such small deviations from the limit cycle can actually be important for synchronization, because again, it is one of these mechanisms that breaks the perfect symmetry in this minimal model of two spheres. And it is it contributes to synchronization, and therefore we included this. And you may think of this that in the simplest model we have just like a bead. The red point would be like a bead moving around a rigid ring.
Right.
And it can go faster or slower. And in this refined model, the bead would actually be attached to an elastic spring, meaning that depending on the hydrodynamic forces, your bead could actually be a little bit more outside from the limit cycle or a bit more inside. And again, for each motion of this, the motion of the red sphere corresponds to a point in this abstract shape space, so it directly corresponds to a Cilia shape. So we can really compute, if this red point moves outside, we can compute how would the cilium change shape and which hydrodynamic friction forces would be associated to this shape change.
So it's basically the spread in the points around the limit cycle is through the noise in the system, right? The active noise. So the compliance is like a measure of how much noise is there.
Yeah, no, but I would rather say the noise can kick you either outside or inside.
Right.
And then there's like a restoring force, like an elastic restoring force that always brings you back to the limit cycle. Because that's the definition of a limit cycle, that after a perturbation, you relax back to the limit cycle. And if you just have a single perturbation, that's what you see. Initial perturbation, then you slowly relax back. And if you have noise that's continuously switched on, you have continuously relaxation back to the limit cycle, but you continuously inject in new noise, and then you see the fluctuations around the limit cycle.
Okay, got it. Thanks.
So there is another question by Kuheli Biswas. Can you unmute yourself and ask the question? Kuheli Biswas.
No, I think they said you should ask the audio.
Oh, I should ask. So maybe Benjamin, I'm reading this question for her. Is the noise in cilia oscillation important for cilia synchronization? If so, how could we understand physically and mathematically? Please ask. Oh, please ask. Okay, I asked the question.
Okay, so cilia noise most of the time has an adverse effect. Cilia noise tends to destroy synchronization, and we see this in models of chlamydomonas synchronization. We see this in cilia carpets. If the noise strength is getting too large, synchronization is destroyed. But the real biological flagella, they are noisy, but the noise strengths are still moderate. So in chlamydomonas, the noise is only 10% of the critical noise strengths where you would lose synchronization. And presumably that's a good compromise for the cell. It is at 10% of the critical noise strengths. It is sufficiently far away from the critical noise strengths where it would lose synchronization. And at 10%, this will be a bit noisy, but that's good enough to swim reasonably straight. And no more effort is needed to get this down further.
Okay, so I had a question, Benjamin. I was wondering that in the last part of the talk, you of course carefully taken care of the hydrodynamic coupling between individual cilia
Yes.
over some separation. But if you, along with that, if I assume that the cilia is since they are all attached to the same membranous bed, so if you also incorporate possible mechanical coupling between them via the membrane, so would that give you a different behavior along some elastic coupling direction? A new direction perhaps will open up in the phase space?
Yes, that's a very interesting question. However, there's no experimental observation today clearly showing that this elastic coupling through the underlying cytoskeleton is important. It's an idea that's discussed right now. For chlamydomonas, it's more direct because you can see in the electron microscope images that the two cilia bases are connected by the distal fibers. And it's not clear how this would generalize to the cilia carpets. And we believe that we should start with simple models and and only once we understood the simple models, then we can add additional ingredients. And even for chlamydomonas, I must say we have a model for the basal coupling, but we also have tons of questions. So I really hope that in the next years there will be more experimental papers classifying the elastic properties of the basal coupling in chlamydomonas. And once these experiments are available, then we can refine our theory just for chlamydomonas. So even for chlamydomonas, we don't understand this fully. And so I think it would be premature to move to a model of a cilia carpet where we include the basal coupling. But already from this model, we can at least say what is the contribution from direct hydrodynamic interactions, and we see how large they are, and we can compare these numbers to a benchmark, namely the noise strengths. And I think that is important, that we not just say, okay, there is some coupling and theoretically that can give rise to synchronization, but we have to ask the question, is the coupling strong enough? Are the synchronization strengths strong enough to overcome the adverse effect of noise?
So I had one more query, sort of, about, I think in some earlier slides you had shown this relationship between the load response function chi with energy efficiency, maybe the dissipated power by input power, something like that. So do you also have some understanding regarding, like, is there a equivalence of fluctuation dissipation kind of relation in this strongly active matter?
Super interesting question, but I do not have an answer. I can only say the classical fluctuation dissipation theorem that we know for passive systems, that is grossly violated here.
Sure.
But we expect this. It's an active system.
Yeah, I was wondering, there are new kind of fluctuation.
Yeah, there's interesting work trying to formulate fluctuation dissipation theorems for also for active systems. Maybe that's possible also for beating Cilia and Flagella, but I don't know.
Also, in this respect, you already connected the response function chi with the energy efficiency. Can you explain a little bit that point? How is these two things connected, the energy efficiency and the response chi?
Yes, and thinking how I best do this, maybe okay, I've been opening a whiteboard. Can you see this?
Yes.
Okay, so in our modeling framework, we assume that there's an active driving force, and there's a force balance between this active driving force and hydrodynamic friction force. Or no, a friction force, and this friction force can be written as a friction coefficient times the phase speed that characterizes how fast the cilium is beating. And now this friction coefficient gamma is the sum of two terms. It's a hydrodynamic friction coefficient. It's really characterizing the hydrodynamic force that arises when the cilium moves, and there's internal dissipation. And in our minimal model, we assume that because we don't know what the internal dissipation is, we just say, okay, we assume it's 1 minus eta over eta of the hydrodynamic dissipation that we would have in a reference case, like for example without flow.
Okay.
And then you have to multiply this with phi dot. And now here I have written the hydrodynamic friction, and this hydrodynamic friction, that is the contribution you would have without flow. And then there can be an additional contribution of hydrodynamic friction forces proportional to the external flow U that you switch on. And the question is now, if you change this external hydrodynamic flow U, if you switch on an external flow, you're adding this extra contribution that I'm underlining to the first term, characterizing the hydrodynamic dissipation. Okay. And if we assume that Q does not change, you see, if this term in square brackets becomes larger, the phi dot goes down, meaning if the friction goes up, you beat slower. Okay. But now if you ask by how much will the cilium become slower, you see, it depends on whether this first term, the hydrodynamic friction, how large this term is relative to the internal friction. So this first term is hydrodynamic, and this here is internal dissipation. And if this energy efficiency either is very small, then the second term, the internal friction, dominates. And then if you're adding here an extra hydrodynamic load by switching on an external flow U, okay, you change the hydrodynamic friction, but the hydrodynamic friction had only a small contribution to the overall friction anyway. It was dominated by internal dissipation, meaning in that case, the term in square brackets does not change much, and the phase speed of the beating cilium almost doesn't change. In contrast, if this energy efficiency would be 100%, then the second term would be 0. There would be no internal dissipation, meaning any change of the hydrodynamic load would, with full impact, affect the speed of the beating flagellum.
Okay. So maybe
from that you can derive that your phase space phi, it's equal to the intrinsic beat frequency minus some coupling coefficient that depends on the hydrodynamic load. In the case of an external flow, you can write the flow speed U, and then you find really that this chi scales with this.
I got the point. So thanks, Benjamin. Looking at the time, maybe we need to wrap it up today. We can, so everyone can, so people can ask questions to today's both the speakers, Benjamin and Brenner, in the Slack module we have created. So thanks, Benjamin, and thanks, Brenner, both the speakers, for the fantastic presentations, and look forward to meet tomorrow.